judge fixed effects or, examiner designs or whatever you want to call it, which is something I've done some work on. It's like a pretty interesting topic and is pretty prolific. It has a bunch of names, like all of these methods that end up getting worked on by lots of applied people, but no econometricians. It's sort of, these have a number of names. So it's called examiner designs is kind of I think the high level appropriate econometric term, but many of the people who work on anything that's in the court will call it like a judge IV. And so you'll hear that, or you'll hear like a leniency IV or a leniency design. And today what I'm going to try and do is I'm going to kind of do two things. So this, like I said, this is kind of near and dear to my heart. I've like worked on this, and I think on one of the papers that was, there were a number of papers before, but this is really increased in terms of the number of papers that have been on this. And so I've had sort of exposure to this. It's really taken off as a result of like the rise of high quality administrative data. So we basically have settings in which we have kind of randomized examiners, or it can be whatever sort of setting you're in. But basically where things are kind of getting randomly assigned. So like loan officers are getting randomly assigned, judges are getting randomly assigned. And what's cool is, we're economists, we're sort of say, all right, well, we have random assignment, we should really try and exploit this in some meaningful way. And I think that's kind of where this has come from. And I'll say that the econometrics literature has kind of struggled to keep up with this. I think there's some new stuff that I'll touch on, but a lot of the work has been in the applied setting, like applied people kind of just making the best of it. It's not kind of like, GMM or something where there's just these huge established set of results, in part because it kind of nests in certain literatures, but it isn't kind of obvious. And so I'm going to try and give you some intuition and some background on what's going on. I'm really going to try and touch on basically 3 points. Hopefully this is sort of true for any design that we're doing, but it's always kind of, we're talking about identification, like what are we getting at? What's the estimand that we're getting at? And then estimation, kind of what's the best approach? And I'm going to really try and advocate for a particular thing. This has been a recent kind of come to God kind of moment, in the sense that I'm like, okay, this is, I think, the right way to do it. And it's not even what I did in my paper necessarily, but I think it's the right way to do it. And then inference, I'm going to briefly touch on this, and I'm going to sort of say, we don't know, but I can at least tell you what referees would want you to do, which isn't necessarily the right thing, but you at least should know what it is. Okay, so let's do this at a really high level first, just for starters. So the way that this, basically to think about an examiner, it's kind of like in Bartik, how I described that there's this thing in which you can say, look, Bartik shows up in a lot of things. Like there's a canonical way in which you can view it. There's kind of these trade versions, but the idea in Bartik, remember that these shares, which varied at the individual level, which kind of aggregated things up. And people were using those shares plus something that was kind of nationally varying or time varying, but in aggregate. And that was kind of how it was constructed. And the examiner design kind of has a similar flavor, in the sense that the idea is that, look, there's an administrator, judge, or monitor, loan officer that plays an important role in deciding some outcome. And so, the examples I gave here, which is just to give you a sense of, there's not nearly as many papers as there are for Bartik, but I think that's in part just because microdata for this has not been as prolific. It's going to be there soon, but it's been used in context for thinking about bail. There's been a really big one. Bankruptcy, getting a loan, so loan officers, parole decisions, disability insurance decisions, patent granting, so these think patent offices, cancer screening, so think doctors doing cancer screening. And in many of these cases, the examiner is effectively randomly assigned. And so what's cool is, in all of this, when we're thinking about this, we've kind of done a lot of work to talk about, look, we think about this in a design-based way, in which, as if there's some sort of design mechanism. We could talk about a counterfactual in which the coin flip went another way, and you all are examiners. So we have 20 examiners in the Zoom, or 18, and there's is effectively some version of a coin flip where one of you got assigned. And there's a wide range. The key kind of component is that there's a wide range of discretion, that you all very much vary in how strict you are in whatever the decision is. So the key ingredients, you have some kind of random assignment of an examiner, discretion this examiner has discretion over some typically binary outcome, and there's heterogeneity in their behavior. It's like not super complicated is the key thing. Once you have the random assignment, people just tend to be different, right? And so there's a nice aspect to which you're just exploiting kind of heterogeneity in a meaningful way. So I'm going to give you two examples just to kind of set ideas if you haven't seen this before. Actually, I'm very curious here. So how many of you, oh, how does this, where's my polls? Oh, here's my polls. So let's pretend leniency design is DAGs. So say yes if you've seen a judge design paper before, or you've read one. Seen is a bit too strong. It doesn't count if you've only seen the abstract. That's like me saying I have read a bunch of papers. Okay, cool. It's like 50-50. I would say it's 50-50. I'm gonna pretend like at least one or two of you are just, I've only seen the abstract or intro. This is like how sometimes I have to keep up in the literature. You have to do that. So I'm going to give you some examples to kind of set ideas. There's some other really neat ones, but I'm going to kind of show you two that are similar in flavor in a lot of ways, but have two kind of distinct things that I think are interesting. I'm not going to go into too much, but I'm happy to chat about. The first one is this paper by Megan Stevenson in the Journal of Law and Economics. I'm using this example in part because Megan actually shared her data with Scott Cunningham for his textbook, the Causal Mixtape. And so the data is there if you wanted to play around with this and look at this. It's available on the textbook website. But in this paper, she's studying bail setting in Philadelphia. So I put the abstract here. I'm not going to read you the abstract, but I do want to kind of describe, because I think this is kind of an amazing literature. Hers is not the only paper. There's been a number of papers that have studied this and found pretty consistent results. So there's the following issue. If you're not familiar with this, if you're arrested, you're held in what's called pretrial detention. So you're arrested, you haven't gone to trial yet, and you're held basically in jail. And the question becomes, well, are you going to be released from jail prior to your trial? This is where people talk about bail, right, as the thing that's being set. What happens is that there is someone who sets bail, and there's typically, the legal arguments about bail are important, but the key kind of distinction here is sometimes you're just held in jail, period. So if you're kind of a risk to everyone in society, say you killed someone and you're apt to kill someone again, there's obviously no reason that you would be released. But a more important distinction is you could be released on bail. They could set a bail of $10,000, or you could be what's called released on recognizance. So this is like you're just released on the idea that you're going to come back. And what they're trying to do is make sure that you come back for trial, right? I mean, it's not like money keeps you from, if you're arrested again, you obviously forfeit the money, but it's basically just a penalty for being able to get out. And one of the big issues that this literature is getting at, this is not going to be relevant for what we're studying, but the point that they highlight here is that what happens is imagine you get held on bail and you're low income. Like if you don't have access to $1,000, you have to pay 10% typically. What happens is that folks basically don't have the money. They're held because they can't afford to pay bail. And so they're held in jail. And what happens is that for a lot of folks, what this literature has basically argued is that for a lot of folks, you're held in jail, say for a week or two prior to your trial coming up. And what your defense attorney will do is if you plead guilty to a lesser charge, for example, you are typically released immediately because a lot of times these are very minor crimes that you're being held with. These are misdemeanors. So what happens is you're held on bail, and then you're more likely to plead guilty as a consequence, because what'll happen is you immediately get out and you don't have to continue to wait in jail. If you at trial then plead innocent, you then continue to wait in jail and not be able to make money, et cetera. Like you continue to wait in jail, which obviously sucks. And so as a consequence, what basically these papers are arguing is that bail causes guilty pleas by keeping people in jail. Is that clear? It's kind of, this is the Y variable is guilt basically, or guilty pleas. And the treatment is basically where you held on recognizance or not. So I don't know how you guys feel. This is like a pretty stark and like horrific example of inequality in the criminal justice system. But the way that you get at the causality there is very challenging without some kind of exogenous variation, right? So if you just look at people who are held on bail versus not, that's the obvious confounding factor that you worry that the types of people who are held are maybe more guilty, or there's a bunch of reasons why you might worry that there's endogeneity. And so in case you're wondering, basically, and this is this nice quote here about what I've had you can wait it out or take the deal and get out conversation with too many clients. That kind of summarizes it. That's the punchline, the public defender saying that. So how did they get exogenous variation? So in this paper, Megan Stevenson uses the fact that there's effectively one of 6 magistrates who see your case. So the magistrates work in 8-hour shifts. There's 6 of them who work in Philadelphia at any given time. And they effectively follow a prearranged schedule where they're basically rotating through times of days and days of the week in effectively a kind of random, they're seeing people at all times of day and all periods of day, in the sense that what you do is you work for, I think it's 5 days on in one particular 8-hour block. And then you do 5 days off, I want to say, and then you rotate into another time block. So you're getting a lot of day of the week variation, time of day variation, and it's effectively random then as a consequence of when you're getting what magistrate you're seeing. The randomness basically occurs as a consequence of the time of day. So you're getting this random assignment of this bail magistrate. But what's notable about this is it's not, for example, that you show up and it's a decision between David and Leland. It's a question of, when in the day you show up, and you kind of need to sort of jury rig how you're going to think about the random experiment, right? It's the randomness is effectively, did magistrate A get assigned in this time of day versus magistrate B? What's a little bit, and sorry, so this is exactly what they say here. And so this is the 3-hour work shifts. Here's the graveyard, the morning shift, the evening shift, and they work in 5 days, 5 off, etc. So this is a paper actually I wrote with Will Dobie and Crystal Yang about consumer bankruptcy judges. This is a little less heavy of an example than like the unfairness of criminal justice. This was trying to ask what's the causal impact of successfully discharging your debt in bankruptcy. So we were Will's job market paper prior to this was about was about the impact of bankruptcy on labor income. This is a paper about kind of consumer financial outcomes. The kind of filing outcomes you can think about afterwards is basically your access to credit and how distressed basically your credit report was. We linked credit report outcomes to bankruptcy records. And when you file, the kind of variation that it's exploiting is that when you file for Chapter 13 bankruptcy, you basically propose a repayment plan to be approved by a judge. A judge basically has to say yay or nay to this. They either approve it and you eventually will discharge your debt, or they'll dismiss it and your debt will be dismissed. Your case will be dismissed. And what happens is that there are several judges who are staffed at a court on a given day. So you show up, and effectively the judge is randomly assigned by the court. There's effectively, randomness that happens. So what happens is basically within a court, a judge will be assigned using a random number generator or a blind rotation within the office. So think of it as you show up and either Daniel or Kanyao, basically there's a coin flip between the two of them, and one of them gets the case and one of them doesn't. And so they use this process in order to build out the dockets. So it's really it's a very easy experiment to think about, right? It's effectively like a coin flip, like we were thinking about in this RCT space. So those are kind of the two examples. I'm going to lean a lot on the second one because I'm very familiar with it, obviously. But those are kind of two examples to set ideas, is that bankruptcy judges or bail magistrates, they're effectively randomly assigned, but we've got several of them. So on average in the bankruptcy courts, there were 3 judges, but there's wide range. Some of the courts had 7 judges and some only had 2. So what gets helpful is, Daniel, go ahead. Okay, so let's get some notation down. I think it's always worth revisiting in the notation, but this is going to be no different than what we did in the IV setting. Now, the only real distinction is we're thinking about a bunch of treatment arms. And so let's consider we have N individuals with two outcomes. So there's the D, the treatment outcome that we're interested in, and the Y, which is, this regular outcome. Think of it as the the credit outcome, think of it as the subsequent guilty plea, etc. And it's very easy to kind of consider the potential outcomes for each of the potential examiners where we only can observe one of the potential outcomes given that there are many potential outcomes, right? So with k equals 2, this is just a binary case, right? It's like if there's only 2 judges, it's no different than if we were just randomly assigning one arm versus the other. We're saying it's the Daniel arm versus the Kanyao arm. It's no different than Moderna and the placebo, right? We've 2 arms and we're comparing one versus the other. The key issue here is that we have many of them and there's no meaningful order right now per se, right? So we were just doing 2. When it's 2, you can always kind of just say, well, there's one versus the other. It doesn't really matter how you think of the intensity of one treatment arm versus the other. When there's multiple of them, then like the question is if you take so I'm just looking at you guys, if it's Daniel, Kanyao, and Kanying, like the point is how do we think about the relative order between any sets of pairs? There's 3 of you, and so there's 3 potential comparisons to be done. What's the relative ordering amongst the 3 of you? It's not obvious that there is one per se. So you can just estimate a number of potential treatment effects. You can look at the relative effect, but it's not even guaranteed that there is an ordering, right? Could be that it's unordered effectively. I mean, the taus have to be different, but it could be that there's a cycle even. So the next question is we can also consider potential outcomes for, say, the guilty plea or for the financial outcomes given a particular examiner, right? And so if we write down that potential outcome in the same way, that looks very straightforward, and we can just estimate the effect of the 3 of you on a given potential outcome. The question is, of course, like, what are we ignoring in this setting, right? What we're ignoring, right, is the potential impact of D on Y. So when we want to do IV, we'll need to consider the potential outcome aspect in which it's, well, the issue, of course, is that, well, DI can have an effect on YI, and since DI is affected by Q, that's kind of that's the channel that's coming through DI. But then there's also the direct effect of Q on YI. And so in order to do IV and have the exclusion restriction be valid, we have to shut down the direct effect of QI in order to do IV. Hopefully that's clear. That's basically no different than when we talked about IV. Really what's sort of going to be important here when we talk about this examiner design is that nothing that we're doing is any different inherently than when we were thinking about IV. It's just a very special case of it that actually tends to show up in a lot of settings. Any questions on that? So let's talk a little bit about the intuition here for thinking about D and Q and W and all these things. So we did all this notation here. So now let's just think about the variation in D across the Q. So Q, remember, is the examiners. So basically conditional on some covariates. W, we're assuming that strong ignorability holds. We're kind of ignoring this problem. We're basically like, look, this is randomly assigned. Let's just pretend it's a coin flip when you show up. So if it was just a constant, that's the easiest case, right? So we're just basically saying we don't need to condition on anything. There's one courthouse, you show up, doesn't matter, you're assigned one of you as an examiner. Then we can consider any of these estimands, right? It's the estiman tau Q prime, which is the effect on D of examiner Q versus Q prime. And that's like, what is the effect of one of you versus another? And that's basically like an RCT, but with judges. You've just got these estimated causal effects. That's really not a problem. And what's nice is you can even talk about like the predicted outcome, right? You can, in this case with no covariates, you can kind of just talk about this mu. This is like the propensity score, right? Remember, this is from when we were thinking about marginal treatment effect. This is like this mu DQ is the propensity score for a given judge value. And then you can talk about the hatted versions as being the corresponding empirical estimates. So kind of concretely, let me just put this here because I think this is useful to start seeing visually. I couldn't really figure out a good way to do it in Beamer, but I think we can do it on the board in some like somewhat useful manner. If I can find any of these stupid pens. Oh my God. course. Oh, there it is. So remember, the idea, the neat idea here now, right, is that, let's just think about this being here. We have a number line now where this is the expectation of di of q equal to q. And so we have, here's mu q, and here's mu q prime, right? And so we can think about these different values here as being these are the effects. And so the relative difference between the two of these is just the estimate of one judge versus the other. That's like, hopefully this sounds very repetitive to you. I'm just repeating a lot of what I've said before, but I'm saying this in part so you understand this, because many of the judge literature jumps to this other piece that is a little bit unusual. So in the context of bankruptcy judges, this mu dq, I guess I put a d subscript here to make this clearer. This mu dq measures the leniency, right? So it's how lenient are you? What's the average propensity to grant clemency or something to an individual? And you could easily measure this in a regression, right? So we were talking about just doing conditional expectations, but that we know that if you dummy out all of them, so let script q be the set of dummies, you go in stata, right? You write stata, you do reg d on I dot q. Every coefficient there is going to be the relative effect. If you do no constant, it's going to get you literally the means in each one of them. Okay. So I was calling this leniency measure. You can get it out. This is this prediction thing that Rosie was just talking about. Given the simplicity of this, these mu d's, these coefficients, these are just the predicted values of the di's from these regressions. And this predicted measure kind of dovetails exactly into what papers have historically used. So here's kind of like, what's the instrument that people have historically used? Hopefully, what happened there? Can you guys see it still? Yeah, okay. Let me just I'm gonna start, this is a little bit weird. I'm doing this in part because I think there's a way that you should do it, but I feel like if I was like, here's what you should do, and then you guys went and saw papers, you'd be like, why does no one do it this way? So what I'm doing is I'm gonna tell you how people do it, and then I'm gonna talk about what that kind of looks like already, and then why it's bad, what I think is bad to do it that way. So in most papers, not all, actually the Stevenson paper doesn't do this. The measure that's been used is kind of this leniency metric for the judges. That is the fitted value, which like Rosie was talking about. You kind of project, you construct a leniency measure, like a fitted D hat, and you use that as the instrument. And so, this is the overall in DGPY, this is this paper that I have with DGPY is what's Adobe, Goldsmith-Pinkham, Yang. It's kind of look at the overall average leniency across judges. So this is, I'm not observation weighting, so it looks different than what you'd get if you just use what exactly is in the paper. I just want to give you a sense of the variation. This is what the overall leniency measure would look like. And so, first, the question is, okay, well, what's the problem with just the overall in the GGPY context? Well, the issue is that judges are not random overall. Like the random assignment metric is within a location and within a time period, right? And so basically the point is like, well, the average judge leniency might just capture location specific effects. And what you need to do is you need to control for the W, right? So the whole point in the bankruptcy case was condition on a courthouse in Western Tennessee. Now you have random assignment. If I look just overall, I don't have random assignment. And so what you do here is you think about this following simple linear regression, now including the W controls. We still have the same dummies. We have the D here. And, these mu hats now are basically equivalent to the predicted values of D once you've residualized for the W's, which is usually going to include the constant. So think of this as like D hat residual from the regression on Q hat residual. So this measure is what is typically called the leniency measure. It's this component that residualizes out for the controls and captures the average variation in leniency within the average of a location. So to give you the simple case where it's like most convenient to think about this is where judges are nested within a court. And so what you do is you're just looking at variation in the leniency measure due to judge-specific random variation. So what this would look like is you have the judge mean, and then you subtracted off the location mean. That's literally what you would get from this regression. You do this and you only focus on the variation that's coming from Q. Is that clear? Does that make sense, Rosie, what I've done so far? This is kind of like this fitted value that you were just describing. Okay, so this is literally what people do, modulus one thing, which I'll describe in a second. So hopefully what I'm making clear to you is like we're like moving back and forth. There's like a regression version. There's like a version where I can do the mean. It's just like a lot of things that people are doing. And what would happen here is you get this thing now where, remember, you don't get to do the level. You get a recentered object that's just around. Remember, this should all be mean 0 because you're subtracting off the average within a location, right? So if you subtract the average within a location, then the overall mean has to be equal to 0. You've residualized out the constant. So this is centered around 0. You still get variation, and it deals with the location average differences and kind of gives the true variation that we see in discharge rates as a result of leniency. And the kind of the point is that, you know, due to the location effect, we can't estimate the true judge leniency, right? We can't estimate the level. So to kind of continue to harp on the empirical example of you all being examiners, if Aslihan and Daniel are in one bankruptcy court and Kanyao and Kanying are in another bankruptcy court, and there's differences there, and the random assignment is only within the courts, there's no way to know whether or not Kanyao is overall more lenient than Daniel. We can only kind of know relative within the court what the relative differences are. And so the thought experiment is always going to kind of be looking at the relative within court variation that we see there. Now, it won't end up mattering if they're totally random. But what you'll end up seeing is that there's just, remember, this is what the overall looked like, and this is what the within looks like. So there's very clearly big differences across locations when you just look at the two histograms. And what's cool is like, we can do the same exercise for outcomes. You know, nothing changes. We have the location and judge effects. We can see differences if we don't account for them. Location variation accounts for a big chunk, but we still see this like variation in the measure. So this is the index measure that we have in our paper, which is kind of like a summary measure of all negative outcomes over the next 5 years. You know, the index is pretty highly varied. There's big geographic variation in the United States, but even within, once you control for location variation, you still see like variation here. Obviously, which judge you get matters. So let me pause there. So the reason why we use this approach, and so why I kind of wanted to emphasize first just how it looked. This is like an RCT, which is cool. Like we have this effect. I think irrespective of the issues I'm going to raise now, if you have a setting in which you have cool variation in examiners that drives big differences in something that's economically meaningful, like obviously it shouldn't be something totally purposeless, but if you have variation caused by economic actors causing big differences in outcomes, that's obviously interesting and important. The challenge is why people really want to use this is they want to know the effect of D on Y, right? We're in an IV world. We were trying to get variation in D from these Q. So what do we need? If you kind of remember, this is, I'm banging you into your head. I guarantee it, if you're a finance PhD and you're taking an exam question from me, I'm going to ask you what these three things are. Remember, you need the relevance. You're going to need to know that the exclusion restriction is satisfied, and you're going to need monotonicity, right? So relevance is pretty straightforward, although we're going to, you know, it's a little bit challenging because you have many instruments here. Like, and so how do we think about the relevance? But the second is that we need the exclusion restriction to be satisfied. So that's, remember that we can shut down this channel here, this direct channel. And finally, we need monotonicity to hold. So we need an ordering in the effects, and we need that to be the same for all people. The last two are kind of the challenging and are not inherently testable. So what I want to do is discuss the issues, but first what I want to do is kind of talk about what's done in practice to kind of give you, this is, Rosie, I think this is going to get to what you wanted to get at, but we'll pause after this. So in many papers, including my own, what's been used is the leniency measure Z rather than dummies for the judge. So I actually skipped over, I like briefly measured. I called this ZI measure to be this hat, this projection. So Rosie made this point, which was like, well, should we like do this fitted thing? Do we have to worry about? Is exactly the problem to in the main. Remember I said with many IV, you worry about overfitting. You have this problem from having many dummies or many right-hand side variables in the 2SLS problem. So there's this fitted value, which is this D hat as the leniency measure that people traditionally have used. So people have traditionally used that rather than doing these dummies. So a lot of papers, what they'll do is they will construct this leniency measure where they'll do some version of what I just talked about here. They'll take like the within judge mean, they'll sort of sum up what the average effect is within a time period or whatever. They'll subtract off the location mean or whatever kind of things that other things they need to control for. And they'll use that predicted measure as their leniency. Now, why do they do that? Let me kind of describe to you why. Speaking as a, if I feel like I'm a reformed leniency user. So I'm trying to describe to you why, as a reformed leniency user, I was using it historically. One reason is it's substantially faster. So when you have a lot of judge dummies, a huge number of judge dummies, especially, for example, in our case, we had something like 110 judges because remember, you're looking across lots of places. So we have many, many judges. That becomes very slow. So it's just really slow versus you construct a single leniency measure. You're just identified and you have one instrument is obviously the claim, right? You've done this fitted thing where you've exactly controlled for it. The second is this visualization point. So plotting the reduced form in first stage against this leniency measure was very intuitive. You were just saying, look, let me look at the outcome and the kind of the bin scatter of this against my leniency measure. And it was really easy to kind of show how these things lined up. Let me actually show you an example. I didn't put this in the slides, but let me show you an example of what that looks like. I think I have it in this paper because I think this, maybe I don't put it. Maybe it's not in here. Oh yeah. So this is why, oh, sorry. So like, this is an example of, I should have put this in the slides. Maybe I'll do that. So like, it's nice. So you're like, oh, awesome. So here is this is leniency on the x-axis. And here's discharge on the y. This is the first stage. You're like, look at how awesome my first stage is. And it's like really easy to visualize. It's very clear what's going on. You can kind of see how much variation there is, etc. So this is like a really clean way of presenting this result that I think people find very intuitive. I should put that in there. I'll do that after. Where are my slides? Oh dear. Here we go. Oh. So, can you still see it? Okay. So the last one is that like people kind of struggle to understand the first stage issue. So this is going to sound very vague. But so when you have those many, many instruments, people really wanted to worry about F-stats. So we talked about this pretesting concern, right? So people wanted to be like, look, I have a very powerful first stage. And when you do it with judge dummies, you run into this issue of, well, how should I think about the first stage power in that setting? A lot of these first stage F statistic tests, like for example, the Olea and Pfluger one that I proposed with the Stock and Yogo, those are harder to think about in the many instrument setting. It's just like not as intuitive of a thing. It really only it makes the most sense in the just identified setting. And so as a consequence, what people wanted to do was have a measure that kind of mapped one-to-one. And when you did this projection, you got this really strong F statistic. I mean, it's like hundreds. Like it's it's comical, kind of what people would report. They'd be like, oh, well, we have an F statistic of 1,000. And so our p-value is obviously 0. And you're like, okay, well, that's probably you're doing something wrong. And it was easier to think about here. And so kind of what I want to emphasize before I get into, there's one last reason why people do it, but that's also not a great excuse, is that the thing to think about here is that, doing it this way, think about our 2SLS estimator. So this was what it looks like when we were over-identified. Remember, GMM/2SLS says, you have the first, you have D, Z, Z prime Z inverse, Z prime Y, and then you have the same thing on the denominator. Remember, these are just the projection matrices, right, under 2SLS? 2SLS, literally, all 2SLS is when you're over-identified. You can be you can be exactly identified, just identified, or you can be over-identified. No matter what, 2SLS is always, from an estimation standpoint, taking the fitted values of the first stage and the fitted values of the first on both the numerator and denominator, and basically multiplying it by the outcome and the first stage. I have done nothing here, right? I've just plugged in for PZ. PZ is by definition hatting it, right? You're projecting under the D space. You adding controls doesn't add anything special. We just would have to residualize the Z's, and we can do a couple steps in order to get that right. That would just get us the D hat residual. And that's what we do when we do the leniency measure. So what it means is that, more or less, using this predicted first stage and using this leniency measure are getting you the same, basically, estimate. They're doing the same estimator, but the inference is going to be very different. And so there's a couple of reasons why I think it's going to matter for thinking about this. But the point of it is to say that, and I'm going to say this out loud, is that there are authors who work in this space who really think of this as being a single instrument. And that literally the only way you can believe that is if you think that all 2SLS estimators are just one instrument, because it's literally isomorphic in this setting. All you've done is this projection. So there's no meaningful way to think about this as being any different. Like the variation we're exploiting is so obvious. I'm sorry, these, by the way, should not be Z's. This should be Q's. These should be those script Q's. Because what you're doing is you're projecting onto the Q space. I hope that wasn't confusing for people. I think you guys got it. But think of these as the Q's, right? Because you're projecting onto the judge dummies. So why is it then that, which is it? I've showed you that there's this equivalency here between the judge dummies and the leniency measure, modulus a couple things. Well, which one is it then? Well, our variation is really the random assignment of the judges, right? I think hopefully it's clear, like when any of these examples I told you, we're obviously using random assignment of judges, examiners, and collapsing to a predicted first stage doesn't change what the variation is. And if anything, it masks the fact that there's this experiment across many different things, not that are potentially reflecting a bundle. So, the estimator is exactly the same. If this was the right approach, we could just do this in every over-identified setting. And trust me, you can. So the issue is with inference, basically how much uncertainty is there in the underlying projections? The point is that if you consider this point here, which is the first stage, remember that there's the true value of these mu's. So imagine now we have we have mu D, Q prime, Q prime prime. This is kind of the first stage that we'd like to use. And we could even think about, and here's like D, right? So there's that, remember that bin scatter graph? Basically the point is to say like, well, the bin scatter should look something like this, right? Sorry, I'll zoom in. I know it's stuck with exclusively brown markers now, since all of my black markers have somehow mysteriously disappeared. So this is the kind of what you'd like for the bin scatter, right? So assuming that lots of things hold, that's what that bin scatter was arguing, right? Is that we have these underlying leniency measures, and here's our D, and so then we have this nice upward sloping thing. But by projecting this linear thing, what we were ignoring is the fact that some of these are better estimated than others, right? So some of our judges are going to be better estimated than others. And when we run the first stage regression on those dummies, we would see that, right, in the standard errors that are on the coefficients for those dummies, right? So imagine, again, we're taking Daniel, Kanyao, and Kanying. We do discharge on a dummy for one of the three of them. Well, if, for example, Kanying has fewer observations, right? So we don't see as many of her cases because maybe she's newer or she just doesn't take as many cases or whatever reason, even if it's still randomly assigned, you're going to be more noisily estimated, right, Kanying? So like you'll just have right, that's all it is. It's just a function of that. And maybe you have higher variance within, like this, that would basically drive the variance in our estimate, right? It's a binary outcome. And so it's, your variance is literally, it's PQ, 1 minus PQ over N is the variance, right? And so as N goes up, we'll get a tighter and tighter estimate of it. But if you have fewer of them, let's imagine you're here. Well, then the true estimate for you could be anywhere between here and here, right? You have a much noisier estimate versus, let's imagine Kanyao and Daniel are much more tightly estimated, for example. And so you'll be closer to the values. The problem is that what you want in your inference is to account for the fact that, this value can change anywhere from here to here. And as you try to fit a fitted line through this in your first stage, it's going to really change the implications for your subsequent IV estimate when you do this, because you'll have sort of more uncertainty in this estimate. This part of the space will be more noisily estimated. And so as a consequence, you'll have maybe larger or smaller standard errors in certain part of the space. Kind of the key idea is to think about the distinction between mu hat D and mu D. In cases when we have lots and lots of estimates, so if we observe 100,000 observations for Daniel, Kanyao, and Kanying, then we don't have to worry about differences there, right? It just kind of converges to the first stage estimate. We have what we would call like the oracle coefficient. But when we have a relatively small number, there might be a lot more issues there. So in many cases, this doesn't end up playing a huge role. Well, the reason is because we have this kind of a lot of observations, but it's not guaranteed in these settings. The last thing that matters in this setting, and this kind of gets, sorry, Rosie, we did like a very long, there was a lot of wind up to get to your question, which is, this is about the overfitting. So the biggest reasons why researchers used the leniency measures, it gave a natural way to deal with the own observation problem. So remember when we were talking about the many instruments and the overfitting, was that you basically, as you added more and more instruments, you would overfit and create bias in the in your 2SLS, in your over-identified 2SLS estimate. We showed that there's a way to show that using the Becker asymptotics. So basically the point is that remember the way that we did those mu hat Ds is that includes individual I's observation in the procedure. If we think about this measure, right? Remember that the estimate for it, when we were just doing the simple version with no coefficients, is that just the sum over I scaled by N of DI, right? Times whether or not QI was equal to Q, right? So maybe you can't see that. Can you see that? I have to look at my own. You can sort of see it. Okay. That there's a single term in there, right? That my own observation in this for the instrument that's endogenous. And so you'd like to kind of not use your own observation. That's the overfitting that Rosie was kind of referring to, that there's an overfitting problem that comes from this. And you'd like to just leave it out. So when people would do this, is that you construct a leniency. It's trivial to do this, right? So if you wanted to construct a leniency measure that leaves out your own, you take the mean and then you multiply by N, right? So that just deals with this. Then you subtract off your own observation and then you divide by N minus 1. And that got you your like leave out leniency that would vary slightly. Every person's, so that would mean that like, say Leland and I both file for bankruptcy and we have Daniel and Kanyao, we'd have slightly, in the data, our leniency measure would look slightly different because we wouldn't be using our own observation, for example. So that's one way in which people try and deal with these things. The thing is that this thing is just Jackknife. That's exactly what Jackknife IV is. Jackknife IV is exactly designed to deal with this, and like showed up in the 1990s and nobody uses it, but it's basically designed to exactly deal with this problem. And so the point is that, you know, if you can solve this issue, all of the things that are valuable for the leniency approach can be solved using existing approaches that make it more transparent and correctly deal with this. I don't really see any great reason to use leniency directly, other than, I mean, I'll be frank with you, because it's translating your results so that researchers who maybe haven't seen the gospel of using 2SLS directly, they're familiar with the idea of this kind of leniency approach. And so you want to kind of know how to translate what's going on. But my case to you would be, for all the reasons we talked about, like Aslan made this point about, well, is it even fair to call it leniency? That using just the judge variation is kind of a much more transparent way to describe what your experiment is going on. And if you want to do the visualization we talked about, all you have to do is just get the first stage coefficients from the regression, right? That's literally, if we run that regression here, let's back a while. If we run this regression and we just get the coefficients on the Q script, those mu's are what we'd want. We just take those coefficients, we put them on the bottom, and then we can put whatever we want on the top. And that will get us the right the right regression values. So that's kind of my case there. And one key issue that was raised, I'm not going to get into it in part just for reasons of time, but it's worth touching. So Michael Kolesar, the classmate of mine at Harvard, his job market paper, he was really touching on this feature that also shows up, and we're trying to work on this problem on kind of making it more coherent. But basically there's the following problem of, remember how I was talking about this number of observations for Kengying and Kenyao and Daniel? It's like, if you had 100,000 observations that you worked with, that makes it really easy. So, because I can we have kind of the oracle estimate. But a lot of times what happens, so in bankruptcy, there's so many people filing for bankruptcy, it's not a problem. But in some settings, you have kind of random assignment of people who don't have a ton of observations. And the reason for this is that there's just, every judge location, there's only a couple of people working, and they actually don't see a lot of things. And so it's a function of how many judges are there relative to the number of observations that are within a location. Because in many cases, what you have is many, many fixed effects, but then you also have many, many judges. And the same projection problem, the overfitting problem that we were talking about with many IV, actually shows up with having many controls as well. And it's for the same reason, because remember that controls are just included instruments, right? So instruments, what we call an instrument is an excluded instrument, right? We exclude it in the second stage, but it's included in the first stage. There are included instruments, which are the controls, and those show up in both cases, and those will actually create kind of the same type of projection bias. The thing is that Michael Kolesar, it's kind of, there's an estimator for this called UJive, which is just a thing that goes on top of Jive, which does a leave one out for your own location as well. So it kind of deals with your leaves your observation out in the control, in the estimation of the control fixed effects as well. And there's code on his GitHub website for this. This is kind of less of an issue, but is definitely something worth looking into. I find this treatment pretty coherent. The jive thing is at least the minimum thing that you can do, but UJive is pretty important with many fixed effects. Okay, let me pause there for a second. Any questions? Okay, so let me I want to give, in the last couple slides, this is going to be like, one of those things like, if you read like the Hitchhiker's Guide to the Galaxy, they're like, so you need to write a leniency paper. Here's what you need to do. So this is at least like what I give you a starting point of, if you guys were going to do this, what do you need to do? And remember, we talked about those three things you have to test. And what I was really kind of emphasizing is with this jive thing is saying like, look, hopefully you agree that this is kind of the right kind of variation. This is a thought experiment, but now we still need to satisfy all these things. So there was relevance, exclusion, monotonicity. Relevance, you can kind of just test by looking and seeing how predictive you are in the first stage. You get good variation. If you do U-jive, just seeing like, do things look reasonable? You know, if you really want to just use the leniency thing, you can propose some crazy thing like your F-stat of 1,000. The more relevant things I think that matter are this exclusion and monotonicity point. So in that setting, it's always really challenging to test this. You can still look for balance, so this is the way that typically people approach this. So in a lot of settings where you have any sort of standard randomized treatment, or you're thinking about something that's, you're looking for, you have something that you think is quasi-random, you can look for balance across covariates that are not relevant for the design. We actually didn't talk about this as much as I should have, but Aronow and Miller, the textbook on the syllabus, they talk about exactly the ways to do this. And just think about when we were doing p-score matching, right? The idea behind p-score matching was to say, what we're trying to do is balance on certain characteristics, those P of X, right? We would estimate some propensity function, P of X, there'd be a P hat we would get, and we'd want to match on that, right? Conceptually, you don't want to compare, by definition, the X's are going to be balanced by definition, right? That's the whole point of the propensity score matching. But what you can do is you can find another set of characteristics that you think are maybe unrelated. So say gender in the context of random judge assignment. What you'd like is that the gender of people who are assigned to lenient judges or harsh judges on average is the same, right? That's the balance between the two. And so what you can do, there's a number of ways to potentially do this. You can do this in two ways. You can either put kind of the predicted first stage on the left-hand side and then run a regression where you put the characteristics that you think should be balanced on the right-hand side. So let me just write this down so that it's clear, because I didn't put it in the slides. So it can be either you have like your, remember you have your mu d q, which is basically the value residualized for the, we'll have those controls. And then you have another set of xi, and then you can have your W controls. And the idea is, you have this predicted value here. This is like your propensity score, holding fixed the controls that you need to for the random design. If this is truly random, then these xi shouldn't be correlated with this measure. Right? Let's go back to the intuition of leniency. Xi shouldn't predict a higher leniency conditional on random assignment, because if it was high, that would be bad. Right? That's one way of doing it. The paper on the right, this is from my paper, the other way to do this, that is potentially slightly easier to do, or can be more transparent, because that makes a like a linearity assumption, is you could say, okay, let me split my p-score to high versus low, and let me just compare the average of some xi conditional on mu d like greater than 0 minus for those where it's less than 0. Right? And so harsh versus lenient, compare the means. It's not very complicated. But this is what this is called balance. And actually, this shows up in lots of settings. You can test for balance in this. This is why I talked about this in the Bardic setting. You can do this, but this is a very generic and straightforward way to at least at the minimum look at what you need to control for. In this setting, we're saying it's randomly assigned, so it better be balanced. And that's what you can basically test for. So summarizing what you're describing is everyone looks the same. 5% of people are observably evil for a subset of judges. Those in the data end up looking like harsh judges because they end up being more punitive to those folks. As a consequence, what we're capturing when we randomly assign the harsh judge to those types of people versus the lenient is we're switching those people. And so what it's going to change is it's going to change what is the late that we're going to estimate is going to be different if we think about that setting. maybe it is actually a good pivoting point, Daniel, to think about monotonicity, which is actually a version, it's kind of the more complicated version of what you just described, which is forget about there being evil versus not. Just some judges, when they see one type of person, they tend to be strict, versus when they think about other type of people, they aren't, and vice versa. There could be, there can be heterogeneity. And so I've been always acting as if there's this line, but imagine there's these multifaceted problems. So this is from that Imbens and Anger's paper. This is at the end, they're talking about different examples where you think about IV and when monotonicity holds. This is from 1994. So suppose the applicants for a social program are screened by two officials. Remember it was Kang Ying and Kan Yao. And they have different admissions rates, even if the admission criteria are identical. Since the identity of the official is immaterial to response, it's likely that condition 1, which is exclusion, is satisfied. It's binary, so it's trivially satisfied. This just has to do with propensity score support. Condition 2 requires that if official A accepts applicants with probability P, and they accept with probability P1, then official B must accept any applicant who would have been accepted by official A. That's monotonicity. It's like this ordering has to hold irrespective of the person. And it's not likely to hold if it's based on a number of criteria. And so their argument is, look, monotonicity as we define it here is going to be challenging in this setting. Basically, this is really tough. So there's no great way to deal with this problem. So what I'll say is the following. There's kind of 3 approaches. So testing for monotonicity is really challenging. So Kitagawa, and then more specifically, this Franzen et al. Paper that the abstract is on the right called Judging Judge-Fixed Effects is trying to think about ways to test this monotonicity approach. I think there's a current limitation in the way that the paper is designed and that about its finite sample approximation. That's getting a little into the weeds. But if you're interested in this, you want to think about this. This is the paper that people are going to know, and it does provide useful intuition for trying to do this. And they talk about this approach. I will say the thing that comes up, and I list this at the end for further reading, if this is something you want to look at. Michael Mueller-Smith talks a little bit about this, in that what you can do is you can allow for differences in the judge's leniency based on observables. So remember, we were talking about conditioning just on the location. But imagine the issue is that I'm worried that Kang Ying is more lenient with, I'm trying to say something that's not going to sound weird. So in bail cases, is people who are doing robberies, she's more lenient for robberies than Kan Yao, but for basically assault, she would be less lenient. So that would be an issue of, if we don't control for that, there wouldn't be monotonicity. We'd be capturing unobserved heterogeneity the wrong way. Compliers may shift, right? We may have defiers and compliers that look different. But what we could do, right, is we could do it within category. If we knew that was an issue, we could say, okay, look within robberies, now do the instrument, and then we weight up across those categories. Then we fix that problem, right? Because we'll have correctly estimated IV effects within category, and then we just weight them up appropriately. So when there's observable characteristics that we think that this is going to be an issue with, that's very dealable. What you worry about more is unobservable heterogeneity in treatment effects. And so the way that historically people have tried to deal with monotonicity is to try and look for tests across these observable characteristics. But this Franzen et al. Paper kind of highlights some of the problems with that approach, but this is something worth thinking about in this setting. It's very doable to deal with it, but it's not perfect. Last thing that I will say is inference in this setting is complicated. Basically, because once you realize there's a many instruments problem, like the econometrician working on many instruments, it's really hard to do stuff with any sort of complicated heteroscedasticity. Homoscedasticity is much, much easier. And I think, frankly, what's too bad is that a lot of the papers that have worked on this have focused on kind of really general problems versus kind of just the judge problem, which is, I think there's a lot that can work there. But kind of the point that I want to highlight to you, this is not going to give you a reference, so I'm trying to work on a paper that will actually give you a reference that says this, is that remember these papers where we were thinking about design-based inference. So we were saying, look, just cluster on the unit of random assignment. So if we only had one court and we had one time period and we're randomly assigning between the 5 of you, you wouldn't do anything weird. You would just use robust standard errors. We'd have treatment effects. Everything would be normal. The only thing that's weird about IV is we're taking, the reduced form and we're scaling it by the first stage, and that creates this weird identification problem. But there's no reason to think that you do anything above and beyond the standard RCT approach. But what seems to be the norm in applied papers is you do this thing where you cluster by judge for reasons that are a little unclear to me. I mean, I've done it in my own work, so I'm not sort of casting blame, but I'm saying that, you know, there's a difference between what is kind of totally supported by like the standard research of like, here's the right thing to do versus kind of what is the norm. And I'm working on a paper with Michael Kolsar and Peter Hull to try and think about this a little bit, but it's worth kind of highlighting like this, it's not totally obvious that you do anything complicated in this setting. And if anything, we might be, by clustering, we might be being overly conservative, for example. And that's pretty much it. I put some papers here at the end to take a look at if you want some good examples. And otherwise, thanks for sticking around for an extra 5 minutes, and I'll see you all on Thursday.